Welcome to the seventh episode of the Introduction to 6502 Assembly Programming. In this episode, we're going to be talking about basic subroutines and jumps. If you haven't watched through the previous slides, I'm going to reintroduce my ish slide. And this ish slide says I know some of the things aren't perfect in these slides. I've kind of simplified some things. So I know there's some imperfections and they were done intentionally, so there aren't difficult questions that come up or confusing things. So if I put this little red ish up on the right hand corner, I know some things are being simplified or generalized that aren't quite 100% accurate, but it's done so for the sake of facilitating understanding. With that out of the way, we have the 6502 address map here that we covered in the last section on the stack, and we're going to be really talking about two of the sections inside this address map today, the reset vector and the stack. Let's talk about the reset vector first, but before that, let's introduce one of the special registers that we talked about before, or introduced before, but never really talked about, the program counter, or PC. The program counter is a register that tells the ALU what the next instruction to execute is. On reset, the value in the reset vector is loaded into the program counter. So whatever value is written to these addresses is where the program will start running. So let's look at an example of that. So let's say we wrote address or value 8000 hex into FFFC and FFFD. What happens on reset is that value is copied over to the program counter, the PC, and in turn, that will become the first instruction that executes. You can load any value you want into this reset vector, and that will be where your program starts running after reset. And it doesn't necessarily have to be 8000. It can be whatever address you want. But that's kind of how the machine starts up. Not really important for most programming. Most people will have this probably already set up in their system, depending on what you're doing. But that's kind of how the system powers up. So don't worry about that too much. It's more important to understand how the programmer or the program counter works. And for that, we'll have a couple more examples. But that's kind of how it gets its initial value. It loads that value from the reset vector. All right, so the program counter, like we mentioned before, tells the ALU what instruction to fetch next, and fetch and execute next. So in this example, we have two instructions over in program memory, starting at address 8000. We have an increment of RAM address 3, and then we have a jump to 8000. So let's look how this works. This is the same example that we had from a previous section, just with one more instruction here. So at reset, the reset vector is loaded into the PC, and in our example before, it happened to be 8000. So the instruction at address 8000 is going to be the first one to execute, and that's the increment instruction. So just like we saw in previous sections, the ALU will read out the value at address 3, which is the 1, and then it'll increment it and write it back, making it a 2. So the ALU executed the instruction pointed to by the PC, the program counter, and completes it, writes back any value associated with it, and then it's done. Next thing that the program counter does is it updates to point to the next instruction. So once one instruction ends, it then is immediately pointing to the next instruction. And I should have an ish tag up in the top right hand corner, but I don't. But anyway, logically that kind of is the way that it works. And So now we're pointing to 8002, and this will be the next instruction that we'll run. And it's a jump instruction. We haven't talked about the jump instruction before, so let's see what it is. The JMP, kind of gave it away already. The JMP instruction is a jump instruction, and all the jump instruction does is loads a new value into the program counter. This value will be the address of the next instruction that will be executed. So here we have an example where the program counter is starting at address 8000, and we have a little program that's over here starting at address 8000. We have an increment of RAM variable at address 3 and an increment of RAM variable at address 4, and then we have a jump instruction to 8000. So let's see what's going to happen here. First thing, the ALU is going to increment the RAM address of 3. Then it's going to increment the RAM address 4. And then it hits the jump instruction. And what the jump instruction is going to do is just load this value back into the PC counter. So we're going to load 8000 back into the PC. And so that 8000 becomes the next instruction that we execute. So you can see we kind of created a loop. It's just going to be an infinite loop here, incrementing both of these variables forever and ever, because we execute those two, then jump back to the start and keep on going. Two items to know about the jump instruction is that, first of all, it can go anywhere in memory. Not all of the instructions in the device that change the flow control are able to do this. It's a unique property of the jump instruction. So that is particularly important to know, that it is more, powerful. It can reach anywhere within in that memory section. Second thing to understand is that it's a one-way trip. So since it just loads the PC counter, you go off, and when you reach your destination, you're there. Unless you have another jump to jump back, then code execution will just continue from wherever you jump to. But that's not always desirable. If you've written any code in other languages, you've used functions, and you call a function, it does its thing, and then it returns back. You come back to where you were. The jump instruction isn't that. It's more of a go-to, which some languages have, some languages don't. The jump instruction doesn't affect any of the status bits, so none of those are updated on a jump. Next, we're going to look at the stack. And the reason why we're going to look at the stack is we're going to introduce the jump store return, the JSR instruction, and the RTS function, or instruction, sorry. These two instructions, the reason why I said the word function, these two instructions are used to create, similar behavior to functions. The jump store return instruction is similar to a function call. It jumps to an address, but then it saves your program counter where you're currently at onto the stack, so that when you do a return from subroutine, the RTS instruction, it pulls that address back off of the stack and puts it on the program counter, and so you return to where you were. Don't worry if, that description kind of didn't make sense. We'll have a visual example on the next page, next slides, to kind of solidify that. But the idea here is that it's a function call and a return from a function equivalently. And these use the stack pointer and the stack RAM. So let's see how this works more specifically with our little friend Ish over here in the corner. So on device reset, we mentioned that we have the stack pointer pointing to 1FF, the bottom of the stack, and the program counter is loaded with the value that's in the reset vector. And in our example, we set it to 8,000, so that's what I did here. Our stack is empty, full of no values, and our program memory is full of code that we want to run. All right, so let's run through this code and see what it does. First thing we're going to do is we're going to do the increment instruction, because that's where the program counter is pointing to. And the program counter will then increment down to the next instruction, which is address 8002. At 8002, we have the JSR instruction with a value of 9008. What this is going to do is tell the ALU to jump to address 9008, but it's going to store the value 8002 onto the stack. So let's watch how that happens. So first, the address, the top part of the address, the 80, gets stored into the stack. The stack pointer, like always, moves to the next address. And then the next value of the address, the 2 part, gets written to the stack. And just like before, the stack pointer will increment up to, or decrement actually, down to the next RAM location. So the address of where we were got stored onto the stack. Then, like we saw with the jump instruction, that's the store return part of the jump store return. But we still have to do the jump part. So 9008, this value here, gets loaded into the program counter, which moves the program counter down here. And so it jumped all the way down here to this section of code. We'll execute this decrement instruction, so we'll go off and decrease the value at address, RAM address 7, the variable that lives there. Program counter will increment to the next instruction, which is our RTS instruction. Now remember, this RTS was returned from subroutine. So what this instruction does is, just like the pull from stack instruction we saw in the previous section, this will pull the return address back off the stack. So just like the pull, the first thing that happens is the stack pointer will increment to the next value, and then read that value and copy it back over to the program counter. So we'll read the 2 out from the first location, and then the stack pointer will increment again to the next location and again read that value out, and we'll have our 82 returned back there. And then the program counter will finish that execution and say I need to go to the next instruction. And so you can kind of see how this created a routine. This was our call. We jumped down here, did some code, and then we returned to where we were, and then started executing at the next instruction. And then the code will continue to execute sequentially from there. All right. And then the jumps, the RTS and JSR instructions don't affect the status bits. So that's kind of how you create functions in the 6502. Really important. So if you didn't quite understand that, maybe rewind and head through that again, because understanding how to create functions or to recognize or read them in existing code, really important. These next slides, less important, so feel free to tune them out. Next instruction is an RTI instruction. It's returned from interrupt handler. An interrupt handler is a special case of an instruction that has interrupts the regular code and jumps off and does something that is typically very time critical, and it has a special return instruction. For most people writing code, they don't need to interact or use the interrupt very much. If you're just beginning, that's typically a bit more of an advanced use case, and I'm not going to cover that in these series of presentations. Maybe I'll add a section on interrupt later, but most people don't need to understand that for a lot of the stuff that they do. Works just the same as RTS does, but it should only be used from an interrupt function. And since I'm not covering interrupt functions, let's move on. Next up in the series will be logical operators. If you've looked at a bit of the 6502 assembly, you'll know that there are a lot more flow control instructions that I didn't cover here. I only covered the jumps and returns, but there's a whole category of branch instructions. I'm going to cover those, but not quite yet. First, I want to cover logical operators, and then we'll talk about comparisons, all the comparison instructions, and then we can talk about the branches. So thanks for sticking with me. If you have any questions, feel free to add them to the comments or reach out to me on Discord. Thank you.